What we'll do this morning again is that we will run through the slides, and then at the end I will get time for questions, and then after the questions, what we'll do is all together we'll get our paper and we will try to write an answer to time. So the question we're going to go through is the August-September 2016 question 7, which is explain the reasons why a pulse oximeter may give incorrect readings. This is the examiner's report. So I've just highlighted this one in orange because that's a pretty neutral statement. The need for an introduction is contentious, but if provided, marks are allocated for the fundamental principles of pulse oximetry. In other words, that I think that when we think about the answer and we think about an introduction, because you can describe the mechanics of pulse oximetry in a lot of detail. But I think the key, what the examiner is sort of keying in here is that yes, you can have an introduction, but keep it brief. And that's what we're going to try to do today with the concepts, okay? Because the basis of the answer is going to be the limitations of the pulse oximetry. And he actually gives you a structure here. Well-structured answers would have organized the facts into 3 main headings: intrinsic limitations of the central processor, incidental errors at the level of the probe, patient factors affecting accuracy of the oximeter. What's interesting is that these 3 main headings are probably not something that you'll see in any of the recommended texts. So there is a bit of leeway in terms of where you can, I guess, slide in some of the things that we're going to be discussing into these sort of 3 sort of factors here, okay? And what we'll do is, I'll go through those things conceptually, and then I think this is where you have to sort of think about it yourself in terms of where you're going to fit those reasons into these 3 categories. So to pass, candidates are expected to provide detailed explanations of various reasons under those 3 headings that might produce inaccurate readings. Now, this is what we need to avoid. So it is not within the scope of this question to define the pulse oximeter or to discuss its uses, advantages, and its importance in clinical monitoring. Similarly, definitions of oxygen saturation and discussion of the oxygen dissociation curve scored no marks. All right, so we just need to be aware of that whatever we write down, we don't go too much into detail about oxygen saturation or trying to define it, and the oxygen cascade as well, okay, oxygen dissociation curve. Common problems include, there were many incorrect interpretations of the Beer-Lambert law and few candidates were able to apply it correctly to pulse oximetry. Although many could draw the absorption spectra of oxygenated hemoglobin and deoxygenated hemoglobin, only one candidate was able to incorporate the curves for carboxy hemoglobin and methemoglobin. And I will show you how today to easily do this. The effects of carboxy hemoglobin and methemoglobin on oximetry will frequently mixed up. Falsely high SpO2 readings from carboxy hemoglobin is not explained solely by high affinity of carbon monoxide to hemoglobin. An impossibly large finger does not affect the amount of light absorbed so much as it prevents proper placement of the probe and creating an optical shunt. So we'll need to discuss what this actually means, an optical shunt. And some candidates propose regular calibration of the machine with a blood gas sample, which is incorrect, and many erroneously used arterial saturations interchangeably for pulse oximetry. And I think this is really important to make that distinction. What is the difference between arterial saturations and pulse oximetry. This is a summary of the examiner's report. So to pass, we need to have essentially this structure here. We need to have the limitations of the central processor, errors at the level of the probe, and discussion of patient factors. To get a good pass, we need to make sure that we explain the Beer-Lambert law accurately and correctly, and also be able to draw the absorption spectra of oxygenated hemoglobin, deoxygenated hemoglobin, carboxyhemoglobin, and methemoglobin. This is the literature review that I used. So you can find all the information that I provided through these three texts. I do find Miller's chapter 41, respiratory monitoring, probably the most interesting and easiest to read. The physics clinical measurement by Mcgee and Tuli is okay. And the second one that I'd use is Dorsch and Dorsch. Dorsch and Dorsch actually has a really good sort of summary. It is quite dry, and there's also a lot of pictures as well, which are probably unnecessary. But I think, you know, for a nice easy read, chapter 41 in Miller's is what I recommend. But again, if you find that time is limited, which is what I'm here for, I've summarized all the important key concepts for this question here. Now, this is where we need to think about the difference between functional saturations and fractional saturations. So there are 5 types of hemoglobins. There's oxyhemoglobin, deoxyhemoglobin, carboxyhemoglobin, methemoglobin, and sulfur hemoglobin. And when we think about pulse oximetry, we are thinking about functional saturations, because the way that it calculates it, and we'll show it, it looks at the fraction between oxyhemoglobin divided by oxy plus deoxyhemoglobin. In other words, the hemoglobin that could potentially carry oxygen, which is why it's called functional saturations. This is compared with fractional saturations, which uses co-oximetry. So co-oximetry is what often you'll find in a arterial blood gas machine. And with a co-oximetry, instead of just having 2 different types of lights, it's got multiple lights, so that it's able to also detect carboxyhemoglobin, methemoglobin, and sulfur hemoglobin. And with all these 3, it's able to calculate what we call fractional saturations. So in other words, functional saturations is what pulse oximetry, so SpO2 is. So let me just quickly write that down. So this would be a representation of SpO2, and fractional saturations would be what we commonly know as arterial saturations from a blood gas machine. Now, the pulse oximetry measures hemoglobin oxygen saturations, so what we call SpO2, using the application of the Beer-Lambert law. Now, with formulas like this, I know that there are symbols that are used inside each one, but I find for myself, and it's a very personal thing, I find that it's easier that I just write what they mean. And the reason I do that is because if I do write the symbol, so I say minus D, this is L, sorry, L times C times E, then I have to go and define it again somewhere else. In other words, I have to go L equals distance, C equals concentration, and then after that you've got like an E somewhere equals the extinction coefficient. I think it's like something like this, extinction coefficient. So instead of doing that, what I do is I just write the actual what they actually mean in the formula itself, just to save time. Okay, that's one of my techniques that I use just to save a bit of time. All right. Now, it's calculated using absorption of wavelengths. This is important to remember, 660 nanometers, so that's red, and 940 nanometers, which is infrared during pulsatile flow. These are the 2 numbers that you need to remember. And look, I think a nice easy way to remember is 660, and even if you say 990, I think that's okay. So if you want to, if you want to think about it in terms of 660, and then you want to think about it as the inverse, which is 990, I think that's close enough, and I think that would be acceptable during the exam. All right, but the numbers are 660 and 940. But a nice sort of memory trick is just to see that they're just inverses of one another. Now, they are selected to maximize, and this is the key concept here. They are selected to maximize the difference between the absorbance ratios of oxy and deoxyhemoglobin.
I didn't get that.
Oh, sorry,
could you try?
It's my little iWatch there. Now, this is the absorption spectra that we need to draw, okay? And a couple of things is on the x-axis, we've got wavelength, and on the y-axis, we've got extinction coefficient. The numbers here that we need to remember are 660 and 940. And if you look here, if you look at the oxy and carboxy hemoglobin curves, they start at approximately 1. And the deoxy and met hemoglobin curves, they start at approximately an extinction coefficient of approximately 5. Now, if you struggle to remember which goes where, okay, just think about the colors. So we know that oxyhemoglobin is red and deoxyhemoglobin is blue. That means that deoxyhemoglobin has to absorb red light, whereas oxyhemoglobin doesn't absorb it and reflects it. And that is why deoxyhemoglobin has a higher absorption spectra, deoxyhemoglobin, than oxyhemoglobin. So oxyhemoglobin would be this one here, okay? And then the other thing that would help you is, why does carboxyhemoglobin give you high saturations? Well, the reason for that is, as you can see at the red point, it pretty much is the same. It crosses over at the same, almost the same point as where oxyhemoglobin sort of crosses here. Okay, so that's one of the clues on why carboxyhemoglobin gives you high saturations. And compare that to methemoglobin. So methemoglobin crosses it at where deoxyhemoglobin at the 660, and that is why methemoglobin tends to trend towards that 85% saturations. Okay, that's why you get lower saturations with that. Now, how are we going to remember this curve? The way that I want you to remember it is, you've got the two lines on the x-axis, which represent your 660 and 940. Have a think about it as with deoxyhemoglobin, okay? We are going down a slide. So it's a slide for a 5-year-old. This is a 5-year-old slide. And deoxyhemoglobin pretty much goes down. It's got a little hump here, and it pretty much goes down like that, okay? With oxyhemoglobin, it's a slide for a 1-year-old. So it's got much less of a gradient, and it looks like a little bit like a sine wave. So, little 1-year-old, less gradient, and you're going to go down and you're going to go up again, okay? And again, this is a 660 and this is 940. And then we're going to put the two together. So you've got your little 5-year-old curve that comes down, a little bit of a bump here. And then after that, you've got your little 1-year-old, which should look something like this. Okay. Now, how are you going to fit carboxyhemoglobin in here? So remember what I said. It's that with carboxyhemoglobin, it pretty much starts just around the same point here. And remember, it crosses here as well. So carboxyhemoglobin will come here and it will come down. And the way I remember carboxyhemoglobin is that it's a bit of a, it's like a C shape. Okay, so C for carboxy, and you look at it, it's got this little, it's a very wide C, but it's like a little C shape here. And when we look at met hemoglobin, what happens is that it starts at where the 5 is, and remember it crosses here, so it goes up, and then it crosses here. And the key thing is it never crosses oxyhemoglobin's curve. So once it sort of comes down here, it sort of follows oxyhemoglobin's curve and looks something like that. All right. And that's how you draw the 4 curves. So I think what we're going to do is, can we practice drawing it? So on a piece of paper, I want you guys to practice drawing it. All right. Can I see whether I can draw it in my book? Yes, I can. Excellent. So what I want you guys to do is draw your axes. This is your x-axis, which is your wavelength. And then have 660, 940, and this is your extinction coefficient. Okay, and the ones you want to put down are 1, 5, and 10. All right, and this is a, yeah, and I think it's a log scale on the graphs, because I think that it starts from like 0.01, and then after that it goes up to like 0.1. So it must be something like a log scale. All right, so now that we've got this here, remember that what I said with the deoxyhemoglobin, it's like a little kid going down the slide. So we've got it here and we're going down the slide. So going down the slide, it's pretty much like that. All right. And then with your oxyhemoglobin, it's a little 1-year-old slide. So it's a bit of like a little curve like this. Okay. And then with carboxyhemoglobin, starts just where the oxy starts just above it. It crosses it here and looks like a C. So it looks something like this. Okay. And then with a met hemoglobin, this is the point here that we need to cross. Comes up, comes down, and remember it then follows the oxyhemoglobin curve. And that is pretty much how you draw the absorption spectras of deoxyhemoglobin, oxyhemoglobin, carboxyhemoglobin, and met hemoglobin. And the other thing that you can do is put your little lines across here like this, and put your little lines across here like this. And as you can see, the reason why these 2 wavelengths are chosen is that the difference between oxy and deoxy is greatest here. And then I haven't sort of drawn it, but yeah, they should actually be, this one should be probably shifted off to the left a little. In fact, what I'll do is I will put the 940. The 940 should actually be here. So that way I can actually highlight the big difference between the deoxy and oxyhemoglobin. All right. Great. Now, this is how a pulse oximeter works. So we've got the absorption from the pulsatile flow, which they call the AC current. And then after that, you've got the non-pulsatile flow. So the non-pulsatile flow includes absorption from non-pulsatile arterial blood, venous and capillary blood, and the absorption from the tissues. And what they do is they calculate the ratios between them both. So it's AC 660 divided by DC 660 divided by AC 940 divided by DC 940. In other words, so the absorption at the pulsatile flow at 660, in other words, the red light divided by the absorbance for the non-pulsatile section, which is from the non-pulsatile arterial blood, venous and capillary blood, and absorptions from tissues. They calculate that absorbance there, and then that's one ratio. And then after that, you've got the absorbance at the infrared light, so 940, and at the pulsatile flow, and then after that at the non-pulsatile flow at 940, and that's another ratio. And then the two ratios between them both gives you an R number. And they have a graph like this. And the R number correlates to a saturation. So like a ratio 1 has a saturation of 85%. And then as your ratio decreases, your saturations go up. I think it's just nice to know just what the graph looks like. I don't think you need to know sort of any further details than that, other than that's how the R ratio is calculated, and then they use a table that is derived from healthy volunteers to calculate what saturations are. Now, tables like this. So this is from Miller's table 41.1, and tables like this are quite hard to remember. So what I've done is I've just deleted the ones that are not important, just to make it a lot clearer for you. So the sources of error include hypotension, anemia, motion, low saturations, methemoglobin, carboxyhemoglobin, hemoglobin K, methHB, indigo carmine, indocyanine green, nail polish, skin pigmentation, possibly sensor contact, and the use of intra-aortic balloon pumps. And we need to have a way to try to think about this and be able to reproduce it in the exam. And I'll show you a little memory trick that I sort of use to do that, okay? Now, just a continuation of Miller's. So it measures, so pulse oximetry measures functional saturation, not fractional oxygen saturations, okay? It's affected by other hemoglobin variants. Carboxyhemoglobin overestimates the pulse oxygenation, as carboxyhemoglobin and oxyhemoglobin share similar absorptions at 660. With methemoglobin, your saturations approach 85%, as methemoglobin and deoxyhemoglobin share similar absorptions at 660. So remember how they cross over, those two curves. The other thing is that calibration is done with normal individuals, and accuracy is limited to saturations more than 70%. And the reason for that is because individuals tend to have variable oxygen dissociation curves, and also at low saturations, this is where you're on the function on the steep part of the curve. Small changes in the partial pressure of oxygen produce large changes in the pulse oximetry. So that's why the accuracy is limited to above 70%. Once you get below this, you get very wide variations because of these two factors, because of variable oxygen dissociation curves, and also because you're functioning on the steep part of the curve. Hypoperfusion will affect your pulse oximetry. So systolic blood pressure is less than 80, any motion artifacts, degradation of your LED lights, venous pulsations from tight placement, severe tricuspid regurg, and arteriovenous shunting. Arteriovenous shunting is a phenomenon that occurs during widespread vasodilation, where you get physiological arteriovenous shunting, so that the venous flow appears pulsatile. Okay. Now, Miller's goes on to describe that pulse oximetry will be affected with anemia in the presence of hypoxemia. And we are gonna just delve a bit into that, because this is where I think the description in Miller's may not be correct, all right? And what I'll do is I'll compare it to what Dorsch and Dorsch has written, and also look at the original article as well. Now with the dyes, methylene blue has a peak absorptions of 668, and so you get saturated on 65%. You note that this is very close, 660, okay, to what methemoglobin and deoxyhemoglobin also absorb, all right? So this is the red light, it absorbs red light so that it appears blue. Then after that, you got indigo carmine and indocyanine green also affecting it. Dark nail polish and coverings, skin pigmentation when saturations are less than 80%. It's a little bit contentious, this one, and I'll just show you an alternate view in Dorsch. Infrared light from image guidance systems and misplacement of probe, not completely over the finger, can lead to an optical shunt. So this is what the examiner was alluding to. With a large finger, you're not able to get it all the way into the probe. And so what happens is that you have a couple of infrared lights that what we call optical shunt. So they just get detected without going through tissues. And this is a source of error for some pulse oximeters. All right. The other name that it's called, and you'll see it in Dorsch, it's called the penumbra effect. And penumbra means partial eclipse. So that's what this is sort of describing. It's sort of like a little partial eclipse where the light source is sort of blocked by the finger here, but then you get these ones sort of coming through. Now, and then intra-aortic balloon pumps also can affect pulse oximetry. And the way it does it is just to do with the pulsatile flow, with the way that the pulsations are different from what the algorithm is. This is a summary of Mcgee and Tuli. So I've just got a page on this. I don't think there's much there that's anything different to what Miller's has written. So they've just said that the limitations are poor function with poor perfusion, difficulty detecting high oxygen partial pressures. You get a delayed hypoxic event detection because algorithms used to prevent false alarms may respond to a noisy or weak signal by holding on to an old value. And I guess you might see that sometimes where, you know, in the event of a sudden cardiac arrest, often you might see the numbers still read quite high, but you'll see that the set trace has flattened. And it's just an algorithm just to see whether that is a true signal or a noisy signal. And you know, that old value might still be there just for a couple more seconds before it sort of disappears. Okay, so there is a little bit of maybe a delayed event detection. And then after that, you get erratic performance with dysarrhythmias, and intra-aortic balloon pumps leads to arterial pressure waveforms that can confuse the pulse oximeter algorithm. So that's what I was talking about. This is a summary of Dorsch. And there is a lot of symmetry with what Miller's has written. So there's inaccuracy from methemoglobin and carboxyhemoglobin. It's inaccurate at low saturation, so similar to what Miller's wrote at less than 70%. From a malpositioned probe due to the penumbra effect, which is known as optical shunting, and venous pulsations, and also using different manufacturers' probe with different chords. Okay. And so with the venous pulsations, remember that the most common example is going to be severe tricuspid regurgitation, or from arteriovenous shunting from widespread vasodilation. Now I want to talk about anemia and in the presence of hypoxemia, because Dorsch says in severe anemia, the pulse oximeter may overestimate pulse, as in the SpO2, in patients with severe anemia, especially at low saturations. And the way that I interpret that is that the pulse oximetry reading will be higher than the arterial oxygen result. This is the description from Miller's. With normal arterial saturation anemia, pulse oximetry has little effect. So it's got little effect on the pulse oximetry reading. However, in the presence of hypoxia, pulse oximetry readings underestimate the arterial oxygenation in anemic patients with true hypoxemia. And my interpretation of that is that Miller's is saying that the pulse oximeter reading will be lower than the arterial oxygenation. So then you go, all right, well, which is correct? Luckily, they both reference the same article. And if we look at the article from Severinghouse, effect of anemia on pulse oximeter accuracy at low saturations. This is the article here in 1990. This is the result. So at a saturation of 53.6%, the mean bias, where arterial saturations minus pulse oximetry of 13 oximeters of 5 manufacturers average minus 15% in a subject with a hemoglobin of 8 grams per deciliter. And I think this is where the confusion is, okay? This a minus 15%. Because I believe Miller's has read this and said that the minus 15% means that pulse oximetry readings must be 15% lower. But the formula here is arterial saturations minus SpO2. In other words, if you go arterial saturations minus 15, you actually get a plus. Okay. So in other words, that the pulse oximetry reading is actually higher. It's actually it's around 68.6%. So from this article here, we can conclude that Dorsch is correct in their description and Miller's is incorrect in their description. Okay, so just be aware of that. And that would make sense because at 53.6%, if you are saying it's 15% lower, that would be a pulse oximetry reading of 35%. And we know that pulse oximeters, once you hit below a certain number, they are grossly inaccurate. And it's not surprising that the pulse oximeter is sort of reading it's trying to read close to 70%, okay, which is probably the limits of where it can actually read in terms of the true saturations, or what it thinks the true saturations are. So other things that Dorsch says with skin pigmentation, although some earlier studies showed that pulse oximeter readings were slightly high in patients with dark skin, newer studies have shown that pigmentation does not make a significant difference in pulse oximeter accuracy. So that's a little bit different to what Miller's has written. And then after that, we've got dyes such as methylene blue and indocyanine green. And then after that, the inaccuracy, the source of interference are optical, electrical, and infrared, nail polish and coverings, motion artifacts, pressure on the probe, reactive hyperemia due to pulsation changes, and also anything that causes probe damage as well. Now this is the way that I think that is a really good way to remember everything. So the way that I think about this visually, you've got a sick Smurf who's blue in a green shirt, trying to get warm with an infrared light and a fire. And the sick Smurf will give you the clues in terms of how to describe the limitations for a pulse oximeter. So the sick Smurf has distributive shock, is hypotensive, is shivering, and has venous pulsations from AV shunting. They're also anemic and hypoxemic, and they're blue from met hemoglobin, anything that a dye such as methylene blue, nail polish, and they've got a green shirt from indocyanine green. Now, they're trying to keep warm with an infrared light, which can cause optical interference. They're trying to keep warm with a fire, which can produce carbon monoxide, and so carboxyhemoglobin would be a cause. And then with the probe on the finger, those are the limitations. So know that the calibration is only done in normal individuals. The accuracy is limited to anything above 70% because of the oxygen dissociation curve. So both due to the variation as well as the steepness at less than 70%. And then after that, you've got probe malfunction. So things like damaged probes or misplacement causing an optical shunt or a penumbra effect. Now, I'll go through any questions now before I go through what I think a structure should be. So I think Meg, you had a question.
Yeah, one of the consultants I've been doing some Viva practice with pointed out to me that in August 2020, ANZCA actually released a statement saying that they believe that SATS probes are less accurate in low saturations in people with non-white skin pigmentation.
Okay.
So I was wondering if that, and I can link everyone to that statement if you want. I was just wondering if that might
yeah, I mean, that would fit in with what,
whether or not you would want to put in the answer.
That would fit in with what Miller's has written. So yeah, skin pigmentation at SATS less than 80%, you might get a higher reading.
And that's exactly what ANZCA said. So they said a disparity widens as SpO2 falls and is more pronounced in individuals with darkly pigmented skin and is likely to be clinically important below SATS of 80.
Okay, so they're following it exactly from what Miller's has written, and that's fine. I think that's that's sort of good to know, and we just need to be able to sort of acknowledge that there is a statement from Dorsch and Dorsch, which says that that this may not be the case. So I think, with this exam, I always have flexibility of thought. In other words, what I try to do is I because of the resources that we all know, that we all sort of read, I actually acknowledge that, yes, some people might think that skin pigmentation may not make a difference. And I'll go to them, yes, because because of where you've gotten that reference from, which is Dorsch and Dorsch. And similar to ANZCA, who says that, yes, it does make a difference at less than 80%, I'll go, okay, then I recognize that that is a statement that you have, that is in symmetry with what Miller's has said. And I think that's okay. I think, it's okay to have to be able to sort of recognize that, different texts may have different statements or different interpretations of the results. Okay. And I think that's
my question then is, would they be more likely to mark us as incorrect, even though the two texts say disparate?
So what I do is when I have that happen, I actually put in the reference. So you'll see sometimes in my answers, when I am aware that there's a point of contention with concepts, I will say that SATS less than 80% might affect the reading, and then I'll put in brackets Miller's. Or if I go that SATS in patients with skin pigmentation don't make a difference, then I'll put Dorsch and Dorsch. That's pretty much how I actually write a couple of my answers, just with specific references on where these concepts are from. So the challenge is now, we are going to have a go writing the answer in 10 minutes, all right? And this is the structure we're going to use. So we want to have a really brief outline of the principles of pulse oximetry. Don't spend too much time on this. And what I think is that, write out the Beer-Lambert law. And the second thing is that we've got to try, practice it, but we're going to try to draw the absorption spectra. And then after that, we're going to have these three main headings. We're going to have the limitations of the central processor, we're going to have the errors at the probe, and we're going to have patient factors. And then we're going to fill in all those concepts I talked about. And I think you have to decide for yourself where you want to put each concept, because I think you can make arguments for each one. All right, but remember that that sick blue Smurf in the green shirt who's getting warmed by the fire, getting warmed by the infrared light, and who's got a pulse oximeter on. Think of that image there, and from that image, you can think about all the different things that can affect the accuracy of the pulse oximeter. All right, so are you guys ready? So let's go. So I'm going to have pulse oximetry first on a second page, because I know that I'm taking the whole incorrect readings result from one limitations of central processor. We're going to go 2 errors at the level of the probe, and a new page 3, patient factors. So pulse oximetry measures the functional HbO2 saturation, SpO2, using the Beer-Lambert law, where the I transmitted equals the I of the intensity of incident light multiplied by Euler's number minus distance times concentration times the extinction coefficient. It's calculated using 2 wavelengths, 660 and 940. This is red and this is infrared. So we've got 660, 940 wavelength nanometers. We got one extinction ratio here. Oops, sorry, I'm going to have 1 and 5. My lines are so okay, so we've got a met hemoglobin, which goes down like a little bit of a slide. Yeah. So deoxyhemoglobin. We're going to have carboxyhemoglobin, like this. That's oxyhemoglobin. We're going to have carboxyhemoglobin like this. Carboxyhemoglobin, and we're going to have methemoglobin. This methemoglobin. Right. So limitations at the central processor. So we need to know that it measures functional, not fractional saturations. It's also affected by carboxyhemoglobin, which overestimates SpO2 as carboxyhemoglobin and oxyhemoglobin share similar absorption at 660 nanometers, and then with methemoglobin, SpO2 approaches 85% as methB and deoxy-HB share similar absorptions at 660 nanometers. Now the other thing is, so this is A, B, but also calibration is done in normal individuals. accuracy limited to more than 70% due to variable oxyhemoglobin association curves and steepness of ODC curve when it's less than 70%. Errors at the level of the probe. So we can say damage to the LEDs, displacement probe, not completely over the finger, leading to optical shunt, penumbra effect, then sources of interference. So they could be motion, such as shivering, optical, electrical, infrared. Now the patient factors, so they would be anemia and the presence of hypoxemia overestimates arterial O2 saturations. And I know that is a point of contention, so I will put in bracket reference Dorsch. Okay. B, so dark skin coloring when O2 sets, when arterial O2 sets less than 80%, overestimates. I know that's a point of contention, so I'll say reference Miller's. C, dark nail polish, coverings, or the use of dyes such as methylene blue or indocyanine green. And that will lead to a decrease in SpO2. And finally, dysrhythmias or use of intra-aortic balloons, arterial venous pulsations can lead to pressure waveforms that confuse the pulse oximeter algorithm. Okay, great. I think I've written enough here. I'm pretty happy with that actually. And, anything that I missed out, let me just have a think. So 660, something that I missed out here. No, I think I've got most things that I want to write down. Great, that's 10 minutes. Was everyone able to draw that diagram after we had that really fun way of thinking about it? Oh yeah,
It's something
That's good.
sort of
Yeah.
I think I got my little bump on that thing there,
yeah.
just like at the wrong spot. I think I tried to exaggerate it too much.
Yes.
I think looking at yours, it was a bit more subtle.
No, so remember that the methemoglobin needs to cross the so it goes up. It needs to cross the deoxyhemoglobin, so it needs to come down and cross it at around 660. Draw the lines, like what I've done. So what I do is I draw the lines up just so that, and the 660 is the most important bit. So the 660 is where I highlight where they sort of cross. And look, on the textbooks, they don't cross exactly there, but just for my memory's sake, it just makes it easier just to sort of think about it that way.